Welcome back. We're going to start this semester dealing with molecular bonding and molecular shapes. In order to predict the proper shape, we're going to have to draw out Lewis structures. These have to do with writing out covalent bonds. So let's just start with a little bit of review. Ionic bonds are between metals and nonmetals, where cations are metals that have lost electrons and have a positive charge. Nonmetals are going to gain electrons and pick up a negative charge, and then they're going to be electrostatically attracted. Those are ionic bonds. That's not what I'm talking about right now. I'm dealing with covalent bonding. And in covalent bonding, the simplest thing is they are sharing electrons between two nonmetals so that both feel 8 valence electrons, or a full valence shell. So here's carbon's electron configuration. That should be easy enough to write out. And looking at that, it has 2 kernel electrons and 4 valence electrons. Fluorine, on the other hand, has 2 kernel electrons and 7 valence electrons. The way we show those valence electrons are with dots. Now we know both carbon and fluorine would like to get 8 valence electrons. Neither are willing to give away the electrons they have to the other in order for that to happen. So they're going to have to share instead to get a full octet, or a stable outer shell. So carbon's 4 valence electrons can be shown by 4 dots. You want to spread those out, thinking about like 4 corners of a box, kind of spread those out. Fluorine has 7, and when you put those around there, the way it was always shown to me was the first one goes here, second one here, third, fourth, fifth, 6th, and 7th. You kind of go around in order. That's not always the way it's going to be, but for right now, we'll kind of say that's the way it's going to be. So we'll put on there our 7 electrons, and there we have them. Okay. Now, you could and you should be able to draw out the Lewis structure of each of these different elements. Now, I would start by, you can do it one of 2 ways. Either know the group they're in, and if you know the group they're in, you know how many valence electrons they have, or write out the Lewis dot structure. So silicon is element 14. It's found in group 14, and everything in group 14 has 4 valence electrons. Here's its electron configuration. The kernel electrons I'll get rid of. So the valence electrons are the 3s2, 3p2, those 4 valence electrons. So that's going to have 4 dots surrounding it. The next element we can look at is oxygen. Oxygen's atomic number is 8. It's found in group 16, so it should have 6 valence electrons. These first 2 are kernel, so the last 6 are going to be valence. That means we're going to put 6 dots around the oxygen to represent its 6 valence electrons. Phosphorus, atomic number 15, found in group 5, should have 5 valence electrons. So here's its electron configuration. Everything except the third level, so the 1s2, 2s2, 2p6, those are all kernel. 3s2, 3p3, those are the 5 valence electrons. And we can represent that with 5 dots. Boron is element 5, found in group 13, so it will have 3 valence electrons. The 1s2 are kernel, 2s2, 2p1, those are the 3 valence, 3 dots. Argon's a noble gas, element 18, so it has, of course, a full outer shell. So the 1s2, 2s2, 2p6 are all part of the kernel. The 3s2, 3p6 are the 8 valence. It has 8 dots. Because it has 8 valence electrons, it doesn't want to lose and won't accept any more, and that's why it has the chemical property of inertness, or non-reactivity. Bromine is a halogen. Halogens are found in group 17, so they would have 7 valence electrons. Now, it's easy for us to get rid of these kernel electrons here, but we have to remember that the 3d is not part of the valence. The 4th energy level is valence, so we got to get rid of the 3d as well. So this has 7 valence electrons, and we'll put 7 dots surrounding it. All right, so that's how you write out the Lewis dot structure. Hopefully you see a pattern, right? And the pattern is, if it's in group 1, they have 1 valence electron. Group 2 has 2. I've omitted the transition metals because they can have variable oxidation states and variable numbers of valence electrons. Group 13, or Roman numeral 3, has 3 valence electrons. Group 14, Roman numeral 4, has 4. Group 15, Roman numeral 5, has 5 valence electrons. 16, 6, 17, 7. The halogens have 8. The exception, helium, has only 2. So the pattern that we see is the group number corresponds to the number of valence electrons. So really, we don't even have to write out the electron configuration. If we know what group it's in, we know how many valence electrons it has. All right, so let's pretend to bond 2 fluorine atoms together. Remember, fluorine is atomic number 9 in group 17, so it has 7 valence electrons. So each of these fluorine have 7 valence electrons, both with like 8. Now there's no reason for the atom on the left to give an electron to the one on the right, or the one on the right to give one to the left. So neither will be energetically stable if they just sit the way they are. So what they're going to do is share. And by sharing those 2 electrons right in the center, right there, then the guy on the left feels 8, the guy on the right feels 8, and those 2 electrons in the center, that's the chemical bond. And so we can draw it out like this. Now, the extra dots around the fluorine are called lone pair electrons. Every 2 dots that you have, every 2 electrons, are a lone pair of electrons around that atom. It's important for you to show those lone pairs because those will become important as we get into going from a drawing of an electron domain to an actual molecular shape. Those lone pairs will contribute greatly. We'll talk more about that in a couple lessons from now. We could also just write this as F2 as a diatomic molecule. They all represent the same thing. Now, let's bond together a carbon and a fluorine. So, as you remember, carbon has 4 valence electrons, fluorine has 7. Neither is willing to give away electrons because they're both nonmetals, so they share. When carbon shares one of its electrons with fluorine, that fluorine feels 8 electrons, and it's energetically stable. It has a stable octet. Now, the carbon went from feeling 4 to feeling 5 electrons, so that's a good thing. If we add another fluorine and we share with carbon, the second fluorine feels 8. Now the carbon feels 6 electrons. If we add yet another fluorine and share electrons, that fluorine feels 8. Now the carbon feels 7 electrons. And finally, we bring on a 4th fluorine, and now that also feels 8 electrons, and now the carbon feels 8. So by this combination, 1 carbon and 4 fluorines, we get a stable compound, carbon tetrafluoride. It would look like this if we draw it out, and it has the formula CF4. It's sharing electrons or distributing electrons uniformly around the molecule, and we're going to learn that that makes it a nonpolar molecule. One of the things I like about drawing these out is we learn what is nonpolar versus what is polar. Later on, when we get to the solubility unit, we'll learn that 2 polar substances will dissolve in each other, 2 nonpolar will dissolve each other, but a polar and a nonpolar won't dissolve. And so we can explain that by looking at the Lewis structures. All right, I'm drawing out a bunch of molecules here, and they don't really mean a whole lot. But what we're going to do is we're going to draw out the Lewis structure for methane, for ammonia, for carbon dioxide, and for sulfur dioxide. And I'll do those for you here in just a moment. And what we're going to end up with are these very different looking structures. And I want to explain why they have the shape they have, because in order to get to the shape, we have to use and draw out a Lewis structure. So there are some rules that apply to this, and as I go through the rules, I'll do the examples. Okay, so the first example we're going to use is methane, CH4. And so it says, sum up the number of valence electrons for all atoms. Well, carbon's element 6, it's in group 4, so it has 4 valence electrons. and then I have 4 hydrogens. Hydrogen always and only has 1 valence electron. So that gives me a total of 8 valence electrons for methane. Now, if I was dealing with an anion, well, those are things like carbonate. If they have a negative charge, I figure out how many electrons are in the carbon, 3 oxygens, and then I add 2 more to that because I have a 2 negative charge. If I have a cation, like in ammonium with a 1 plus charge, I figure out how many valence electrons nitrogen has, 4 hydrogens, and then I subtract 1 from that number because it has to have a positive charge, so I lose 1. In this case, we're not dealing with anions and cations, so it doesn't apply. Then it says predict the arrangement of the atoms. Usually the first element is the center, oftentimes carbon, never hydrogen. Hydrogen can only make 1 bond, so it's never in the middle. So we put carbon in the middle. Then it says make a single bond, 2 electrons between each pair of atoms. And so I have 1, 2, 3, 4 hydrogens to attach. And so I do that with a single bond. That counts for 2 electrons. Then let's see how many electrons I've used. 2, 4, 6, 8. Remember, I have 8. Now, the carbon feels all 8, so it has a stable octet. Hydrogen only can feel and wants to feel 2, so it's okay as well. So at this point, I am done. That is the molecule methane, CH4. And if we look up here, that's what I wrote for CH4. I just drew a single line around each. Okay. Next, let's move on to ammonia, NH3. Okay. So I'm going to get rid of what we have here. So we have a little space. And so if I'm dealing with ammonia, NH3, nitrogen is atomic number 7. It's in group 5, so it has 5 valence electrons. And I have 3 hydrogens. They each have 1. So that's 8 valence electrons. So I've got that number. Next, it says, I don't have to worry about anions and cations. Predict the arrangement. Hydrogen's never in the middle. Well, that means nitrogen is going to be in the middle. So we put that here. And then we use a line to add the hydrogens. So hydrogen, hydrogen, hydrogen. At that point, I've used, each line is 2 electrons, 2, 4, 6 electrons. I have 8. So it says arrange remaining electrons to satisfy octet. Remember, I have 2 more electrons. I'm going to go ahead and put them right here. Now, the nitrogen feels the lone pair on the top, those 2, plus the 3 single bonds. So it feels 8 electrons, and each of the hydrogen feels 2. So we're done. Now, this is its electron domain geometry. It has 4 domains, a lone pair and 3 bonding pairs. Now, it turns out that that lone pair is going to move around and repel these hydrogens down. So if I really were to look at this in the real world, these hydrogens get pushed down from the lone pair on the top. So in this drawing, if you imagine this is me standing here, that's my head with my eyeballs in it, my little body, and then my arms are the hydrogens sticking out. Well, those electrons on top of my head push down my arms down from straight out down toward my hips. And so this would have a tetrahedral electron domain geometry of a predicted 109.5 degree molecular shape. But that's not what we get. Instead, we get this shape, trigonal pyramidal, and it has a bond angle of about 107 degrees because this lone pair of electrons pushes down the hydrogens. Now, we're getting a little bit into the weeds here, but that's what molecular geometry is about, using the Lewis structure to predict based on how many are bonding, how many are non-bonding electrons around a central atom. Okay, so more to come on that in the next few days. So we just did the ammonium up here, NH3. That's ammonia right there, isn't it? Right? Now I said we'll do carbon dioxide next. Okay, so with carbon dioxide, it's a little bit trickier, CO2. Carbon has its atomic number 6, group 4, has 4 valence electrons. You got 2 oxygens, they're element 8 in group 16, so they each have 6 valence electrons. So 12 plus 4, I got 16 valence electrons to deal with. 16 valence electrons. No cations, no anions. So it says predict the arrangement. Carbon oftentimes is in the center, so I'll do that. So let me get rid of some stuff here. So I want to put carbon in the center. Now, don't write carbon, oxygen, oxygen, okay? We always want to go with symmetry. Mother Nature likes symmetry. So instead, let's go carbon, oxygen, oxygen. Keep it symmetrical. Now, we've used 4 electrons, and if you remember, we said we have 16 electrons for carbon dioxide. So then I have to try to arrange the remaining electrons to satisfy that. So I've used 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Now, that's how many electrons I have. Each of the oxygens feels 8, but the carbon only feels 4. So therefore, I have to try something else. So the next step says place electrons in pairs, lone pairs. Well, I've done that. If you have too few, because I only have 16, I need more, it says form multiple bonds. So now I'm going to do the same thing. I've got my carbon, but I'm going to make a double bond and a single bond. And I'm going to see what happens now. Now I've accounted for the double bond is 4 electrons and the single is 2. So that's 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. That's all I've got. The oxygen on the left feels 8 electrons. The oxygen on the right has 4 from the lone pairs. The double bond's another 4. It feels 8. And the carbon now feels 6, so we're getting closer. So now let's try to make 2 double bonds. Now I've used 2, 4, 6, 8 electrons, 9, 10, 11, 12, 13, 14, 15, 16. Now each oxygen feels 8 electrons and the carbon feels 8. This is the structure we're going to get. It's perfectly symmetrical, and that makes it a nonpolar molecule. And we'll talk more about polarity in other days, right? If you were to divide this up and look at it symmetrically, so we'll divide it like this way and this way in quadrants, it's perfectly symmetrical everywhere you go, and that makes it nonpolar. All right, so let's go here. So we just took care of now our carbon dioxide, this one here, and now finally let's look at sulfur dioxide, SO2. So let me erase what I've got. So for sulfur dioxide, you have 1 sulfur. It's in group 6, so it has 6 valence electrons. You got 2 oxygens. It's also in group 6, so they each have 6. So we have 18 valence electrons here to deal with. So let's go ahead and do this. I won't click on the things. We'll just put them out. We got sulfur, oxygen, oxygen. And we want to complete the octet. We've got 18 electrons. We've used 4. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And at that point, both of the oxygens feel 8 and the sulfur feels 6. So I've seen this game before. I know I need a double bond. So I go sulfur, double bond, oxygen, single bond, oxygen. That's 2, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Now the oxygen on the left feels 8, the oxygen on the right feels 8, and the sulfur feels 8. Now what's important to remember here is that lone pair of electrons, this pair right up here, is going to push and repel these other lone pair electrons and push them down. So we end up getting a structure that looks like this, where it becomes bent. It's not linear. Now, another piece of the puzzle that we need to understand is this. I made the double bond on the right side. I could have just as easily made the double bond on the left side, and we would have got this for a structure. Now, it turns out that the best answer is both of these structures exist simultaneously. We call this idea resonance. Now, let me explain it a little bit further. A single bond is two electrons being shared. Two electrons. It tends to be a weak bond and a long bond. A double bond is four electrons being shared. It is a stronger bond, but a shorter bond. Now, I'm going to make up these numbers. I'm going to say a single bond is 2 centimeters long, and I'm going to say a double bond is 1 centimeter long. Well, it turns out if I were to make the molecule sulfur dioxide and freeze it so it's solid, and then look at it, I could do what's called X-ray crystallography, and I could take a picture and I could literally measure the bonds, and I'd find out that this bond right here and this bond right here are both 1.5 centimeters long. They're exactly halfway between a single and a double bond. And what that means is the electrons are switching between the right and the left oxygen and sharing. So the way we really draw it is this. That dashed line means that the double bond, single bond is flipping back and forth in resonance. So you can either draw this resonance structure or both of these structures for SO2. Now the key here is not to lose track of this. When I had CO2 and when I had SO2, they might look very similar on paper, but CO2 comes out to be linear and SO2 comes out to be bent. So this is a bent shape, this is a linear shape. And that's really the point of us drawing these Lewis structures, is trying to figure out what is the shape of the molecules going to be. Okay? Now, I'm just about ready to stop here. What I would suggest that you do is, I have here 8 molecules for you to draw out the Lewis structure for. A couple of them, nitrate and carbonate, have a charge on it, so you have to take care of that. Remember, if you have a negative charge, you got to add electrons. Try to draw out the Lewis structures on your own. Tomorrow, we will go through them. Now, on the PowerPoint, because if you're still watching and get frustrated, you can pause now, but you see I put all the answers on there for you, so you can pause and check and see if those are the answers you got. Okay? All right. Well, thanks for joining me. I want to just get this lesson out there because I know some of you had a hard time logging in today with the weather and the first day of the semester. Thanks for joining me. Have a good day. Bye-bye.